Alright, so we've talked about that when we add and subtract radicals, they must be like. Same index and same radicand. So what happens if they're not like? For example, I have the square root of 44 plus 2 square root of 99. Right now that looks like we cannot add those because we have a 44 and a 99. Now, at this moment, we really can't add them because they're not like. But those radicals are actually not simplified. So before you decide whether or not they are like radicals, you must have them in the simplest form. So you have to simplify those radicals as much as possible, then decide if you can add them. So this 44, I can multiply, or I can factor out a 4 times 11. And right away I see that 4 is a perfect square. So I'm going to take those 2's out. Same thing with the 99. It's 9 times 11. And I can take the 3's out because that's a perfect square. So I rewrite square root of 44 as 2 square root 11, right? The 2's come out, the 11 stays underneath, plus, don't forget this 2 here out front. I'm going to multiply it by what I take out. So I'll have 2 times 3, right? Square root of 9 is 3. And then I have an 11 left underneath. I'm going to simplify that real quick and get 2 times 3 is 6 square root of 11. So after I've simplified these radicals, I can see that they are like. I have 2 square root of 11 plus 6 square root of 11, and I get 8 square root of 11. Alright, let's look at another one down here. Again, it looks like they're not like. None of these match. But I need to simplify them. 50 is 5 times 10, which is 5 times 2. I see a square I can take out. A is not a perfect square, so I have to leave A underneath. 2 times A, that's factored as much as possible. Nothing I can do there. 36 is a perfect square. I don't even have to factor that. I know the square root of 36. Let's rewrite what we have. So square root of 50A, I can take out those 5's. Square root of 25 is 5. I'm left with a 2 and an A underneath the radical. 2A. The middle term I can't change. The last term, the square root of 36, is 6. And I still have an A underneath the radical that didn't have a perfect square. I look for like terms. I see 5 square root 2A and 3 square root 2A. There's like terms. 5 minus 3 is 2 square root 2A. And the minus 6 square root of A stays the same. No more like terms. That's as far as you can go. Alright, go ahead and try the examples on the right-hand side. Okay, part A says the square root of 8 minus 6 square root of 2. These are not like, but they're also not simplified. 8 is the same thing as 4 times 2, and 4 is 2 times 2. I see a perfect square. Square root of 2 squared is 2. Right? You can take this set out. There's still 1, 2 underneath the radical. And I can't do anything with the negative 6 square root of 2. So now they're like. 2 square root of 2 minus 6 square root of 2 is negative 4 square root of 2. Right? 2 minus 6 is negative 4. And square root stays the same. Alright? Now I have square root of 20 plus square root of 18 minus the square root of 45. None of these look like, but none of them are simplified. So I start by factoring 2 times 10. 10 is 2 times 5. I see a pair. I can take those out. 18. 2 times 9. 9 is 3 times 3. I see a pair. I can take that out. 45 is 5 times 9. And again, 9 is 3 times 3. It's a perfect square. I'm going to rewrite this how I can by taking out all these perfect squares. The square root of that 2 squared is 2. And I have a 5 left underneath the radical. And the square root of 18, I can take out the pair of 3's. Square root of 9 is 3. And I have a 2 left underneath the radical. And on square root of 45, I can take the square root of 9 and get 3 and have a 5 left underneath the radical. I look for like terms. I see 2 square root of 5 minus 3 square root of 5. Those are like. 2 minus 3 is a negative 1 square root of 5. And then plus 3 square root of 2. Nothing I can do with that. And you could choose to write this 1 here, or just write it as a negative square root of 5 plus 3 square root of 2. Either way would be fine for me. That's as far as you can go because square root of 5 and square root of 2 are no longer like, or are not like. Alright, let's throw some variables in there and some different roots. Now I've got the 2 times the square root of 3x cubed minus 5x times the square root of 27x plus 4 times the square root of 3x. Alright, this last term, 3 times x, nothing to factor. That's as far down as that will go. This 27x, 27 is 9 times 3, and 9 is 3 times 3. So I can take out a pair of 3's. In the first term, 3 times x cubed, the 3 is as far as it can go. But the x cubed, I can break down into x squared times x, and then pull out that x squared, because we're looking for perfect squares that we can take the square root of. So let's go ahead and rewrite this. I'll have the 2 that was already out front times the square root of x squared is x. What's left underneath? A 3 and an x. So square root of 3x. Minus, I still have that 5x out front. It's going to get multiplied by, well, the square root of 3 squared is 3. What's left underneath? A 3 and an x. So square root 3x. And we said that 4 square root of 3x was as far as it could go. I apologize, this is going to get smooshed in here. 3x. That's a plus in between. Alright, so let's look at this. They're all like. I have square root of 3x, square root of 3x, square root of 3x. I'm going to start by just adding these two. Actually, hold that thought. I'm going to multiply that 5x times the 3. So 5x times 3 is 15x. Let's take another second to rewrite. 2x times square root of 3x minus 15x, right? 5x times 3, square root 3x, plus 4 times the square root of 3x. So let's start with these two. 2x minus 15x would give me negative 13x square root 3x plus 4 square root 3x. Now here's the tricky part. Yes, they are like. I have a square root of 3x and a square root of 3x. But when I go to add the coefficients, or the numbers being multiplied out front, I have negative 13x plus 4. But 13x and 4 are not like. So essentially what I'm going to do is I'm going to factor out this common factor. Right? So if I divide out a square root of 3x, I want to know what's left. If I take out square root of 3x, I would have negative 13x plus 4. So you can see I'm trying to add them, but I can't really add them because they're not like. And then I have that square root of 3x that we pulled out as the GCF. So that was a GCF that we pulled out. And yes, usually we write the GCF out front, but with radicals, we don't want anything to look like it's under a radical if it's not. So I like to write the radical second. But that would be as far as you can go on that type of problem. Alright, this last one here. Now we're talking about a cube root. So important to pay attention to the index. So cube root, we're looking for triplets. Something times itself 3 times. When it comes to variables, we want multiples of 3 for the exponent. For example, this x to the 6th. That is a perfect cube. I can take that out. The y to the 4th is not a perfect cube, but I could break it up into y cubed times y, right? So here's a cube, and I'm going to have 1y left over. And 2 times y, nothing we can do with that. So the cube root of that 2x to the 6th, y to the 4th, I can take the cube root of x to the 6th, and we take 6 divided by 3, we get x cubed. The cube root of y cubed, we're cubing it, and then we're taking the cube root, we end up with just y. What's left underneath that cube root? A 2 and a y. And there was nothing we could do with that second term. So now they are like. I have a cube root of 2y and a cube root of 2y. But again, it's the same issue as the last one. I'm adding x cubed plus y to 5, and they are not like. So all we can do is write it in this kind of factored form of x cubed y plus that 5, and then the common factor, the GCF, of the cube root of 2y. And that would be as far as you can go. So there you go. That's how you add radicals that are not like. You must make sure they are simplified as far as possible first, and then look for like radicals.